Hey guys, Mr. Janowski. This is part 5 of the chapter 35 slides. In the last part, we learned KVL and KCL, Kirchhoff's voltage law and Kirchhoff's current law. In this part, we're going to learn how to actually use those in a pretty sophisticated way to deal with more complicated circuits. So let's get started with that. So first, what is Kirchhoff's current law? The most useful way of stating it, as far as I'm concerned, is the total current flowing into a junction must equal the total current flowing out of that junction. So in this case, you've got I coming into here, and you've got I1 and I2 going out. So what that tells you is that I must equal I1 plus I2. And the flip of that on the other side. I1 and I2 are coming in, I is going out. So over here, that tells you I1 plus I2 must equal I. And then what is Kirchhoff's voltage law? This is the law that deals with the loops. So if you have any closed loop going around a circuit, all of the gains plus all of the drops must equal 0. So in this part, we're going to learn how to use those, excuse me, in a trickier way to deal with more difficult problems. So you can have circuits that aren't actually in series or in parallel. So if this guy here, if V2 were a resistor, then you could just, combine these in series, combine those in parallel, and then the whole thing's in series. But that battery messes everything up. So we can't treat these guys like parallel or series circuits because nothing's in series or parallel. So how are we going to figure out what the currents are and what direction the current is flowing? So it's time to apply KCL and KVL. So when you're doing this, the first thing you should do is name your currents. So my habit is I start at the left. I call the first one I1. So I've got I1 coming out of here and going this way to this junction, which also, by the way, tells me if I1 is coming out of this battery, I have to have I1 coming into the battery. That is another use of KCL, the conservation of charge. So anyhow, I1 coming up to here. At this point, it splits. I'm going to call the part that goes down here I2, and this other part. There's a lot of different ways to do this. There's 2 different ways to do this. 2 is not really a lot. A lot of people would say call this branch up here I3, and you can totally do that. The problem is then you would end up having 3 unknowns, I1, I2, and I3. I think it's much better, instead of doing that, apply KCL at this point and say that if I had I coming into here and then I2 is going out here, then what's going this way must be what's left. In other words, I1 minus I2. So maybe that seemed goofy the first time you learned it, but the beauty of doing it this way is I still only have 2 unknowns that I've got to figure out. And that means when I get to the system of equations part, I only need 2 equations. If you named a third one, you would need 3 equations. So anyhow, first part, name your circuits. Name your currents. So here's me saying use KCL at this point, so you don't have to invent another unknown variable. So you will see sometimes these things called partial currents. So the current flowing through here is I1. The current flowing through here is I2. So those are just currents. But when you're talking about what's happening here, what's flowing through this resistor, what's flowing through this battery, it's not I1 or I2. So in this context, for the light blue part over here, I1 and I2 are what are called partial currents. It's not the actual current that's going that way. You think of those as sort of the parts, the components, in a sense, of the current. You may see that term again if you go further in physics in college. So we've drawn our currents. We've guessed which way they went. Didn't even spend a lot of time guessing which way they went. I just always draw them the same way. They're coming up from here, and then they're splitting at this point. Now we've got to draw our loops. And I highly recommend always coming up with one way to draw your loops and always using that way. So I like to start lower left, and then go clockwise. And I always start lower left and then go clockwise. I don't even care which way the current is actually flowing. I'm just making my kind of guess and I'm sticking with it. It helps cut down on mistakes. So, how do you do the loop? You've got to start. Let's do loop A first. So I'm going to start here lower left and I'm going to go up this way. The first thing we get to is V1. And V1 is a gain because I'm starting at the negative terminal and I'm going to the positive. So if you go through a battery negative to positive, it's a gain. You're gaining voltage. The next thing you get to is R1. So because our loop is going through R1, the same way that we drew the current, I1, that's going to be a drop. If you go through a resistor with the current, it's a drop. And then loop A continues. We come down through here. Now we get to R2, and we're going through R2 the same way as the current I2. So this will also be a drop. And then nothing happens. You get back to the beginning of your loop. So you have this equation right here. From here, put in the numbers. Everyone is sloppy when they do the units here. I mean, maybe I should be writing 15 volts minus 10 ohms I1, but don't even bother doing that. So you put in the numbers, you get it down to an equation. Get your unknowns in order, I1 and then I2, and then get the voltage on the other side. So yeah, I end up with an equation here that has two unknowns. So it's a rule in math. If you have two unknowns in one equation, you can't solve it. So then you do loop B. So going through loop B, start at the lower left, and you get to R2. Now this time, notice loop B is going up while I2 is going down. So we're going through this resistor against the current. So what does that mean? If you go through a resistor against the current, you actually have a gain. So the next thing that happens, we come up here, we get to R3, and our loop is going with the current I1 minus I2 through a resistor. So that's going to give us a drop. And then we get over here to V2. So we're going through a battery, but we're going from the positive terminal to the negative terminal. So that battery ends up also being a drop. So you do this, you do the algebra. Be careful with all the small math, especially negative times a negative. Make sure that ends up being a positive right here. And you get another equation. So we now have a second equation with two unknowns, which that equation is also unsolvable. So what do? I'm giving you time to think. I would solve this with elimination. There's lots of ways you can do it. I would go with elimination. This is a system of equations. Yeah, you could solve one and then sub into the other. Elimination is the best way. Matrices are a nightmare. So they're wonderful, but they're also a nightmare. Don't do it the matrix way, Finkel. So we're going to use elimination. The way we're going to do it, we're going to multiply the top equation by 3. Then we're going to add the top equation down with the other equation. The I1 terms are going to disappear. We now have 110 I2 equals 70, which gives us I2 is equal to 0.63 repeating amps. So from there, you take that number, you sub it back into either of the equations, whichever one you think will be easier. So I picked the top one, subbed it in, did the algebra, and it ends up that I1 is equal to 0.2272. So yeah, we've been doing math for a while. Maybe we've lost the plot. What were we actually doing? We're trying to figure out the current going through each resistor and the direction, which means we've got one more thing to figure out at this point. We have to figure out what is I1 minus I2. So you plug in your answers for I1 and I2, and you end up with a negative current, which is kind of weird. What does a negative current mean? So a negative current means the current that I drew going this way, so clockwise around here, is not what's actually happening. What's actually happening is we have a current going the other way. So I guessed that I1 minus I2 is going left to right through R3. What this is telling us is that it's actually going the other way. It's not a negative number going this way. It's a positive number going this way. So it's going counterclockwise through here. So again, That's not a big deal. I'm not mad at myself for guessing wrong. It doesn't matter. You're way better off just quickly making all of your guesses, always guessing the same way, and just anticipating that some of your guesses will be wrong. You'll end up with negative numbers, and then just relying on the fact that, well, I can just interpret that correctly at the end. So that's how you do it. So lots of different ways to check your answers. You can plug the numbers back in, is a good way to do it. And if you do it correctly, you should end up with something like 0 equals 0. That's true. Over here, 0 equals 0. That's true. If you end up with some number that isn't 0 equaling 0, that means you goofed in your algebra somewhere, you made a mistake. So go back and start over. So if you wanted to, you could go ahead and analyze this circuit fully and figure out, well, what's the voltage across each resistor? What's the power being used by each resistor? It wouldn't be that hard. If you go on to physics in college, you'll probably have to do that. But I am not going to make you do that, at least not in circuits like this. If you've got these complicated ones, the ones with 2 batteries where you can't simplify them, you just got to do this system of equation stuff. I'm not going to make you go the whole 9 yards and figure out all of the things. You will have to figure out all of the things in the other circuits, the ones that you can simplify all the way down, but not in this kind. So when we did this, we ended up with I1 minus I2 is negative, which means this guess was wrong. So the current isn't flowing into battery V2. It's not flowing into the positive terminal of battery V2. It's actually flowing out of there. So the question is it ever possible to have a positive current flowing into the positive terminal of a battery? So think about that for a second. And the answer, is it ever possible? Is yes. You do that all the time. That's what you do when you charge your phone. You're forcing a positive current into the positive terminal of the battery. So yeah, I bet you do that several times a day. So again, quickly, the steps. If it were the kind of circuit that you had to simplify, if things were simply in series and parallel and you could, boil them down a little bit, you would go ahead and do that. I'm not going to give you problems like that. These problems are long enough as it is. Next thing you do is you draw the currents. So draw them and name them. And you're just making guesses at this point, and just be consistent in how you do this. And my recommendation is use KCL to minimize the total number of currents you're drawing. So call this one I1, call this one I2, and don't call this one I3. If you call it I3, that gives you 3 unknowns. You would need 3 equations. You could draw another loop. You could get another equation using KCL if you wanted. But you're better off minimizing the number of unknowns you have to solve for. So yeah, first draw your currents, name your currents. Next, draw your loops. So always do it the same way. I recommend starting lower left, going clockwise, and just always do it that way. And again, don't really spend too much time thinking about, well, this battery's bigger than this one, so the current's probably going this way. Just always draw them the same way, and then you figure it out at the end how everything was going. So after you've drawn your loops, you use KVL to come up with a couple of equations to create a system of equations that ultimately you can solve. Remember the rules for gains and drops. It's a gain if you're going negative to positive through a battery, and it's a gain if you're going through a resistor against the current you drew. The flip side is it's a drop if you're going from the positive terminal to the negative terminal of a battery. And it's a drop if you're going through a resistor with the current that you drew. So you use the loops, you get 2 different equations, and then you solve your system of equations using, I'm going to recommend using elimination, but lots of ways would work. And then you go back and you check your answers. So here are the steps, just written a little more simply. And that's it for part 5. So hopefully this was helpful.